The final lesson we'll be covering in Chapter 2 is Lesson 2.7 on using absolute value functions and transformations. We talked in the last chapter, at the tail end of Chapter 1, about absolute value equations. Absolute value equations we solved were things like the absolute value of 2x plus 5 is equal to 8, for example. These were absolute value equations because there was only one variable. All right? So in this chapter, we've been using the idea of linear equations in two variables, x and y, and looking at the results of those on a coordinate grid. And so today we're going to be spending some time taking a look at absolute value functions, functions involving x and y that also have an absolute value. All right, so an absolute value function is a function that uses f of x equal absolute value of x. And so again, we can also use y here instead of f of x if you want to, but it's just some function, and again, it is a function, so if you go back to all what we talked about in the first chapter, or the previous part of this chapter, you know, again, a function is something that should pass the vertical line test. You know, each input has exactly one output, all of those kinds of things. The vertex of an absolute value graph is the point, the maximum or minimum of the absolute value function, and I'm just going to put the point that the function turns, and I'll put max or min in parentheses. Okay, it's the maximum or minimum. We've talked about, way back in Algebra 1, we talked about the vertex of a parabola, and that is the point at which that parabola turns and goes the other way. Absolute value graphs are going to have a different shape, but they're going to have the same kind of feel. They're going to have a point at which it turns and goes the other way, and we call that point the vertex. A transformation changes, some sort of a transformation. You guys have done transformations back in geometry. We talked about transforming a point and moving it to a new location. So it's no different here. Transformation changes the size, shape, or position or orientation. So changes the way a graph looks. Okay, it might move it up, it might move it down, it might move it left or right, it might stretch it, and then we'll get into some of those things in just a little bit here. A translation is a vertical or horizontal shift of a function. Okay, a vertical or horizontal shift of a function. So if a function is moved 2 units right or 2 units up or whatever, that's going to be a shift, and we call that a translation. A reflection essentially is going to reflect a graph about some line. Typically when we talk about absolute value graphs, we reflect them across the x-axis, and you'll see there's some symmetry involved that already reflects them somewhat across the y-axis. But a reflection is simply you know, something that mirrors or flips a function's graph. Okay, and your English teachers will be proud if you actually remember to put an apostrophe in there. Okay, so a reflection is something that mirrors or flips a function's graph. So where it may flip it upside down, it may, you know, we're not going to do too much with rotations right now. But anyway, so those are the key terminologies that we'll need as we go through this. Again, you can always look in the back of the book and get something a little bit more specific, but I think these definitions should be sufficient. And so we've talked about parent functions before. We talked about the parent function of any linear function. The parent function of any linear function is just simply y equal x, right? The most simple function we can possibly look at. And then as we start to incorporate things like slope and y-intercept, the y-intercept shifts the graph up or down, and the slope stretches the graph, you know, again, changes the slope of that graph. Well, it's really no different when we look at an absolute value graph. It says the parent function for the family of all absolute value functions is y equals f of x. The graph is a V-shaped, okay, it is V-shaped, and it is symmetrical, and that's a key word there, symmetrical about the y-axis. Again, the parent function is symmetrical about the y-axis. For every point xy on the graph, the point negative xy is also on the graph. And let's think about those points, for example. You need to change this in your text because this should say 2, 2, not 2, 0. If I look at a point over here, and I don't like all the 2's here, so I'm just going to choose this point right here. How about negative 1, 2, 3, 4, up 1, 2, 3, 4. So there's negative 4, 4, and here is positive 4, 4. And here's the point 2, 2, and here's negative 2, 2. Negative 3, 3, and positive 3, 3. So again, think about the absolute value function. If I have the function f of x is equal to the absolute value of x, if I do f of 3, well, f of 3 says the absolute value of 3, which is 3. F of negative 3 is the absolute value of negative 3, which is also 3. So the inputs of 3 and negative 3 both have the same output of positive 3. And that is denoted by these 2 points right there and there. All right, and we could do the same for 2 and negative 2, 4 and negative 4, 1 and negative 1, etc. All right, now the point that we kind of can think about a little bit too is the point 0. If x is equal to 0, my function is then f of x, or f of 0, is equal to the absolute value of 0. And see, there is no positive or negative 0, whether you put, again, so when you do absolute value of 0, you get 0. All right, the highest point or the lowest point of an absolute value function is called the vertex. Vertex helps to spell, right? Vertex of an absolute value graph, and I'm just going to put abs val. You guys know what absolute value is. And then the vertex of the graph is the point 0, 0. In this case, it's 0, 0, because it's that point right there. That's the point at which the graph stops, turns, and goes the other way. All right, so that's the most basic parent function of all absolute value functions. Now, the next piece of this then says, all right, well, that's kind of boring all by itself. Now let's start looking at what happens as we start to do some different things to that graph. Again, as we change the slope of the linear function y equals mx plus b, that stretches the graph to have a slope of whatever that number is, and the y-intercept moves that y-intercept up or down on the y-axis. And so we took the function that was y equal x, and we moved it up 2 units, and we took the slope and made it negative, and so you got this graph here. But we somehow manipulated the parent function y equal x. Now we're going to manipulate the absolute value parent function and see what we get for results. All right. Transformations for general graphs, and this applies to absolute values. It applies to quadratic functions, which we'll talk more about later. It actually applies to circles. Some of you guys this may sound somewhat familiar to you when we get into a little bit later on in the lesson, if you remember graphing circles in a coordinate plane from geometry. All right, so when a is greater than 0, the graph is stretched. Okay, the graph is stretched. And again, this is for general graphs, not specifically for absolute values. We're going to be able to look at some specific cases when we look at absolute value in just a minute here, but let me go through this first. And then again, it says it is stretched, and y equals absolute value of absolute value of x is going to be narrower. So if a is more than 1, we're stretching the graph out, and it's narrower. So again, f of x equal x looks something like this. If a is more than 0, then the result of that function might look something more like this. We stretch it out, so we make it narrower. And again, I'll get into some specifics about what you do with that. Again, assume both of those go through 0, 0. If a is less than 1, then the graph is vertically shrunk. And y equals a times the absolute value of f of x, absolute value of x, is wider. And so if we multiply by something that is going to be less than 1, then you get something that's more like this. Kind of flattens that graph out a little bit if it's less than 1. All right, so the way that I like to think about absolute value graphs is this. When we try to graph an absolute value function, when we try to graph one of these things, the best way to do this is to recognize the fact that this number right here and this number right here are going to be stretches or shrinks of that function. All right. Now, I want you guys to recognize, and you have to change this in your notes, and I apologize for this because I didn't recognize it until just as I'm going over this lesson. This is missing something. There should be absolute value there and there. Otherwise, it's not very much fun, right? So, in looking at that, we were looking at graphing y equals absolute 1/3 times the absolute value of x, and y equals -2 times the absolute value of x, and then compare them with the parent function y equals absolute value of x. So the graph of y equal 1/3 absolute value of x is a graph of absolute value of x, but it is vertically shrunk. Okay, because this number here is less than 1, it is a vertical shrink by a factor of 1/3. Now, to make this much easier, we know that y equals absolute value of x. As I look at that original function, remember we were talking about it's all of these points, 1, 1, 2, 2, 3, 3, 4, 4, etc. And so the slope of this side is rise 1, run 1, rise 1, run 1. Okay, the slope of this side is 1. Okay, over here we're looking at points like, -3, +3, -2, +2, -1, +1. And so these ones are all down 1 over 1, down 1 over 1, down 1 over 1. And so the slope over here is equal to -1. And so the parent function of the absolute value graph has a slope on the right branch of 1 and a slope on the left branch of -1. Okay, those numbers are opposites of one another because, again, this slope has to mirror or be symmetrical with this slope. So what I'm going to use then is I'm going to use that idea of being 1/3 as big. And so if I think about the absolute value of x, I'm going to graph absolute value of just x, the parent function. I'm going to graph that in black here. Okay, and so the absolute value of x looks something like this. All right, so there is the parent function, f of x equals absolute value of x. And now I know that the absolute, or 1/3 times the absolute value of x is going to be a shrink of that. And this number, that's the coefficient here, what that's going to be now is that's going to be the slope of the right branch. So again, if my slope is 1/3, I'm going to rise 1 and run 3. And I'm going to rise 1 and run 3, and I'm just off the page there. And so now I'm going to go ahead and connect those, like that. And the slope of the left branch has to be the inverse, or the opposite of that. And so on the left side, my slope has to be, so this has a slope of 1/3. The slope over here has to be -1/3. And so we can rise 1 and run -3. Rise 1, run -3 if I put that negative in the bottom. And now you have a graph of y equals 1/3 times the absolute value of x. Okay, you can see that this graph is shrunk. All right, this is a shrink of the original graph. Okay, it sort of stretches it out and it makes it wider because the function has 1/3 of the slope of the original, and the original had a slope of each side of 1. All right. The next thing we're going to take a look at is the absolute value, or -2 times the absolute value of x. Oh, by the way, to fill in the rest of these boxes, the graph has a vertex of 0, 0. All right. And because we've now said that the slope is 1/3, we're going to rise 1, run 3. It's going to go through the point 3, 1 and -3, 1. All right, what about the next? We said the graph of y equals -2 absolute value of x is the graph of y equal absolute value of x vertically, but it's vertically stretched. It's vertically stretched because that number there is 2. That number is bigger than 1. I know what you're thinking. Well, Mr. Lowe, it's -2. That's less than 1. But let's think about the magnitude of that number. That number is 2, and so we're going to stretch that graph by a factor of 2. The negative, remember from the very first page we talked about reflections, the negative here is going to reflect the graph across the x-axis. Now, if you want to try to remember all of that business, again, it's going to still go through 0, 0. All right? We can do that, and we can try to remember all of this, but what I want to do too is I want to go ahead and graph the parent function again. And again, you can do this every time if you want to, just so you have something to compare it to. There's the absolute value of x. Now let's take a look at the, using that idea that this number out in front here is the slope of the branch on the right side. Again, you've got two lobes of this thing, if you will. All right. And so the right side of this thing has a slope of -2. So starting from the origin, we're going to go down 2 over 1, down 2 over 1, down 2 over 1. The left branch of that, since this one has a slope of -2, since that one has a slope of -2, you can probably guess that the slope on the other side would have to have a slope that is +2. And so if the slope is to be +2, that means that I need to get a slope of 2 to get to this origin. So what we can do is we can say, all right, well, that's down to left 1, down to left 1, because now when I move from left to right, I go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And so that makes our graph. We've got a couple of points to use, and we can go ahead and graph those. So you notice the slope of that branch on the right side has a slope that's +2. All right, and the slope on the slope on the left side has a slope of +2. The slope on the right side has a slope of -2. Now notice that we did a couple of things. We flipped it upside down because now the slope of the right branch is -2 instead of +1. So we've now reversed this thing and flipped it upside down. So that's our reflection. And we stretch the slope by a factor of 2. All right? So this number out in front of the absolute value will always stretch or shrink my graph. So again, this is going to go through the point 1, -2, and -1, -2. All right, so let's go ahead and graph our checkpoint problem here. I want you guys to try this one, see how it goes, and we'll come right back and start our video again. All right, so the original parent function y equals absolute value of x looks like this. So here's my parent function. All right, my slope of the right side and the left side is +1 and -1. Again, that has a slope of 1. This has a slope of -1. The leading coefficient of my absolute value sign is 3. And so the slope of the right branch of my transformation is going to be 3. So we'll just pick a different color here. Now I'm going to, from the origin, rise 1, 2, 3, and run 1. 1, 2, 3, and run 1. And I'll use those 2 points, those 3 points rather, to make a graph of the right side. That's the right branch. And again, since this is +3, the slope of the right side is +3. So the slope of the left side leading into that would also then have to be a slope that is the opposite of that. And so over here, I'll have to have a slope of -3. All right? And so now all we do is we just say, all right, well, to get a slope of -3, I can rise 3 and run -1, rise 3 and run -1. And then I'm going to use those points to connect. And so now you have the left branch as well. Notice the slope of the branch on the left side is -3. The slope of the right side is +3. All right. So what happens if we do some other stuff in here? All right. Now there's all kinds of other things that we can do to this absolute value function. All right. And so we want to take a look at graphing y equals a times the absolute value of x minus h plus k. All right. General form of this. All right. Now this kind of reminds me of when we talked about graphing circles back in Geometry B. So if you remember that, recall that at all, this may be helpful for you. If not, then potentially you might be learning this all over again. But this number that is in the absolute value, this number that is in the absolute value, because it's inside of a grouping symbol, we're going to do the opposite of this number to x. All right, because it says take x plus 2 and then take the absolute value. That's going to force this graph to be moved 2 units to the left. The -1 on the end is simply going to affect the y value. And so this is going to move it vertically. This will be our vertical translation. And then the leading coefficient is our stretch and or reflection. I'm just going to put stretch and or reflect. And we only reflect if that number is negative, which it is in this case. All right? And so the general form of this vertex form of a parabola, is this guy right here. Y equals a times x minus h plus k. This number inside of the parentheses is h. That's my horizontal shift. And remember before I said it's the opposite, right? It's because the original formula says it's x minus h. And so we're going to be doing the opposite of positive 2 to get it to say negative 2. And if you're reading this little key over here, this is kind of helpful. It says identify the vertex. Rewrite the original function as x minus negative 2, because in the format that we have to have it in, it's going to be minus negative 2 to get plus 2. All right, so we're going to use that information. We're going to identify and plot the vertex. So since this says plus 2 here, that means that we're going to be moving this thing. Since it says plus 2 there, that means we're going to be moving this thing 2 units to the left. Again, it's always opposite when it's inside of grouping symbols. And then the minus 1 on the end is your vertical translation, and that's not inside of a grouping symbol, so we're just going to do what it is. So our vertex gets moved to the point negative 2, negative 1. This is going to be my turning point of my absolute value function. All right? Now, recognizing the fact that what we just talked about is this number right here, that tells me the slope of the right branch. So the slope of the right side is negative 3. And so from this point then, from our vertex, we're going to go down 3 over 1, down 3 over 1. And we'll go ahead and connect those points with a line. There's the right side of my absolute value function. Now that's the right branch. The left branch will have a slope that is not the reciprocal, the opposite of that. So the m of the left side equals positive 3. So that's positive 3 over 1. So we're going to have to find a way to go up 3 over 1 to get to this point. So if I just go down 3 and left 1, now I know that this one will have a slope of rise 3 over 1. So down 3 over 1 again. And there is your absolute value graph. All right. So we wanted to plot a point, and again, I'm not going to pick the point so much. I'm just going to use my slope. But if you went 1, 2, 3, 4, this point right here is negative 1, 4, negative 1, negative 4. And so if we pick the point like negative 1, negative 4, and then use symmetry to point another point, so that's on the other side of this. So that's going to be at negative 3, negative 4. I don't really do it with symmetry so much. I do it with the slopes. So this step might not be as valuable as doing it like this, looking at the slope of the right side and the slope of the left side. All right? And then obviously you're going to connect those points with a line with a V-shaped graph, which we know all absolute values are, and we kind of already did that. In comparison with the absolute value of x, the graph of negative 3, absolute value of x minus 2 minus 1, is the graph of the initial, and it is stretched. It is stretched vertically by a factor of 3. Then it's reflected across the x-axis because of the negative out front. The negative flips it across the x-axis. It's finally translated. Let's see, we're going to probably put this left 2 units because of the plus 2 within the parentheses or within the absolute values. And then finally it's going to be moving it down 1 unit. All right? So once again, recognize the fact that I know this looks like a big old mess here, but if you go back to the original absolute value equation and the general form of that, which is right here, again, the number in the absolute value moves your horizontal graph right or left. And again, it's always opposite. The number after moves it up or down, and then the leading coefficient A was what represents our stretch or our shrink. All right, so let's slide on down to this next example, and let's see if we can't use that to our advantage. First of all, this one has a vertex of 3, 2. Okay, our vertex is at the point 3, 2. So that means this thing has been shifted right 3 and up 2. So describe the transformation first, and then, so that, because again our vertex is at 3, 2, that means that it's been shifted from the origin right 3 and up 2. All right? So it says the equation has the form y equals a times x minus 3, because it's been moved right 3 units, and plus 2 because it's been moved up 2. Now I know some of you guys are looking at this and going, wait a minute, right 3 is plus 3, why are you using minus? And I have to refer you back to the previous equation on the top of the page. And remember I said whatever's in the parentheses is always opposite. So what's in the absolute value is the opposite. Since we're adding 3, moving it right 3, we need to have x minus 3 on the inside. Now, It says substitute the coordinates of a point to calculate the slope. Look, I'm not going to calculate the slope this way. To me, this is kind of worthless. We're not going to do all of this business. All we're going to do is we're going to take a look at the graph and say, what's the slope of the right branch? Because we know that A is equal to the slope of the right side. All right? And so if I calculate the slope, I just pick this point, and then I find another point right on the grid and another point right on the grid. To get from here to here, I go down 2 over 1. So my slope is negative 2 over 1, or negative 2. So that number is my A. And again, we calculate the slope of the right branch. What do you suppose the slope of this branch is? Well, if you've answered m equals 2, then you are absolutely correct. Again, we go up 2 over 1 because those two should be opposites of one another, positive 2 and negative 2. So my absolute value graph is y equals negative 2 times the absolute value of x minus 3 plus 2. All right, again, this was the reverse. This was a reflection. This was the 2, which stretched your slope by a factor of 2. This minus 3 moved it right 3, and this plus 2 moved it up 2. Okay? All right, so let's try a couple examples on the next page, a couple of checkpoint problems that you're going to try, and then we'll come on back and we'll talk about this general transformations of general graphs, and this should make a lot of sense to you after we've looked at some of these. Okay, so this number in the absolute value is going to be my horizontal translation. Since it says minus 1, we're going to do the opposite, and so that means we're moving it right 1. The minus 2 on the end says we're going to move it down 2, and the negative 1/2 tells me the slope of the right side is negative 1/2. Okay, we're stretching, or I'm sorry, in this case we're shrinking it and we're inverting it. Okay, we're going to reflect it across the x-axis because of the negative here. All right, so we all got a lot of stuff circled here, but let's start on our vertex. And again, because of the minus 1, we're going to move it right 1, and because of the minus 2, we're going to move it down 2. And so there's my new vertex. My graph is going to be V-shaped coming into that point. The slope of the right branch is negative 1/2. So from here, if my slope is negative 1/2, that says rise negative 1 and run 2. Rise negative 1 and run 2. All right, so I've got a couple of points there, and I'm going to use my line tool to connect those dots. And so there is my right side graph. Like we talked about, the slope on the other side should then be the opposite of that, which is positive 1/2. And so to get a slope of positive 1/2, I'm going to go down 2, left 2, down 1, left 2, down 1, left 2 a couple of times, and then I'm going to use that to make the other side of my graph. And again, if you want to clean some things up here, you can go back in and clean some of this stuff up. Okay? So there is a graph of negative 1/2 absolute value of x minus 1 minus 2. Fairly painless, like I said, once you kind of get the hang of it. The big thing is recognizing that this number right here is always opposite. Okay? So let's go ahead and let's try one more example. Let's write an equation of this graph. So first of all, we identify the vertex, and the vertex has been shifted left 1 and up 3. So we're going to write the general form of the absolute value equation, leaving some space for a. All right, and then having our absolute value here and have our x there. Now, this is moved left 1, okay? So if I put negative 1 in here, negative 1 would result in moving it to the right 1 place. So we have to change this to plus 1. So again, x plus 1 will be a result of moving it left 1 place, because again, it's opposite. It moved it up 3 units, and so we should have a plus 3 on the end. And now, very simply, all we have to do is we have to calculate the slope of the right side of this thing. So if I look here, I rise 2, run 1. Rise 2, run 1. So the slope of the right side is 2, and so my leading coefficient is 2. If you wanted to look at it, the slope over here should be negative 2, down 2 over 1, down 2 over 1. But there's the absolute value graph of that picture. All right, so the equation is 2 times the absolute value of x plus 1 plus 3. All right, so in general, transformations of general graphs, all right, when we talk about any graph, not just absolute value graphs, if I take some original function f of x, okay, or some original function y equal f of x, and we use this same idea, the number in the parentheses is going to result in moving this thing left to right, and I'm going to put opposite or oppo after it. All right, left or right, and it's the opposite of that. The plus k on the end is my up or down. And again, the number out front is my stretch. Now, we've been talking about the slope of the right branch, the slope of the left branch, all that kind of stuff. What we've been doing is, again, the original parent function, y equals absolute value of x, the leading coefficient here was 1. And so if I wanted to say y equals 3 times the absolute value of x, we'd say the slope of the right branch is 3. Essentially what we did is we multiplied the original slope 1 by 3. So we stretched it by a factor of 3. So it's no different here. We just, again, our parent function has a slope of 1, so when we multiply that by this coefficient a, we know that our slope is going to match. Okay? So again, the same idea here. It says stretch or shrink the graph y equal f of x by a factor of absolute value of a if a is not equal to 1. If the absolute value of a is 1, it's going to stretch the graph. And again, why are they using absolute value? Because we're just saying the magnitude of the number. If the number is bigger than 1 or less than negative 1, we're going to get a stretch. Okay, the negative is what's going to reflect it. So again, reflect it. Well, let's finish up this thought first, sorry. So we're going to stretch it if that number is bigger than 1. If the magnitude of that number is bigger than 1, we're going to shrink it if it's less than 1. All right. If that a number is less than 0, basically if it's negative, that's when we are going to flip the thing upside down. And then we're going to be translating that unit, or translating each of those points, or the points of the graph horizontally, h units, and vertically k units. So this is all exactly the same thing, right? So we haven't done anything new. It's just kind of, generally speaking, instead of using, the absolute value of x plus h, we're using some other function. And I have no idea what these functions are on the next page here. Okay, we're going to apply some transformation to a graph. So we're going to be looking at applying a transformation to this graph right here. All right. I don't know what the function is that made that graph. All right. But the first thing that I want to do is I want to say, look, what happens if I were to multiply that graph by a half? Well, the only thing that we've changed here is our a value. Our a value is a half. So all the y values are going to be half as big. Before, the slope was, if we were doing y equals 1/2 times the absolute value of x, all we would do is we made the slope of the right side and the left side half as big. And so that helped us to make our graph. In this case, now we're going to do this exact same thing, but being a little bit more specific to it and saying, look, we're taking half of all the function values f. And so we're not flipping it, we're not moving it, we're not doing anything else to it. It says the graph of y equals 1/2 times f of x is the graph of f of x, but it's shrunk vertically by a factor of a half. All right, so basically what we're going to say is it says to draw the graph, multiply the y-coordinate of each labeled point in the graph by 1/2 and connect their images. So basically this point here on the new graph is going to be half as high. Well, right now it's at 4, so half of that's 2. The x values don't move left or right because there's nothing else in the parentheses with x. It's just simply f of x. Okay, when we get to our next example, there's going to be something more to that. All right, so we're going to take half of the y values, or half of the function values. This one here is at 1, so we're going to move it down to a half. And this point here is at 1, 2, 3, so we're going to move it to 1/2. Let's see if I can do this with my pen here. And so there's a graph of half of f of x. Basically, we just took half of all the f values. All right? Now, the next one's not quite so easy. I'm going to go ahead and wipe this off, so if you need to pause your video to finish writing, please feel free. And so let's go to the bottom of this example and let's look at the graph of y equals negative f of x, or negative f of x minus 1 plus 2. So as we said before, this number in here is my horizontal or vertical, my horizontal move. And so this moves all my x values right 1. This shifts them all up 2. This leading coefficient here of negative, again, that's a negative 1 here, right? That is simply going to be a stretch, or in fact a reflection by a factor of reflection across the x-axis. All right, so we've got a whole bunch of different stuff here. Let's deal with that negative first. It says this graph is a reflection in the x-axis. Okay, so we're going to reflect it across the x-axis. Then it's translated right 1 unit, because again, it's the opposite of what's in the parentheses, and up 2 units. To draw the graph, first reflect all the labeled points and connect their images, then translate and connect these points to form the final image. So I'm going to kind of do it all in, well, I'm going to do it in a couple steps. The first translation says to flip these and put them down below. So the reflection, which is the first step here, I'll go ahead and do that in blue. We were up 1, 2, 3, 4 units. Now we should be down 1, 2, 3, 4 units. This point was up 1, so now it's down 1. This point was up 3, and so now it's down 3. Whoops. Let's try that one more time. Down 1, 2, 3. Now we're doing this from the x-axis because that's what we're reflecting about. All right, so don't just count down 3 units from here. Count down 3 units from the x-axis. So the first look of that thing is going to be something like this, and you can see basically the negative f of x basically flips it across the x-axis. Now take all of those points and move them right 1 and up 2. So now I'm going to change colors here and say if we're going to do the right 1 and up 2, from here I'm going to go right 1 and up 2. Right 1 and up 2. Right 1 and up 2. And now I'll use my line tool and connect those dots. And you can see that we have the exact same graph, but we've reflected it across the x-axis because of the negative here. We had to reflect across the x-axis. All right. Once we reflected across the x-axis by doing the negative, that gave us our blue graph here. All right. And then we followed the negative 1 plus 2, and that moved it right 1 and up 2. So from there we went each point right 1, up 2. All right. So the last checkpoint problem, you can go ahead and try on your own. Pause your video, give that a shot, and then we'll be right back and taking a look at this example. Okay, so to have this, to go ahead and reflect this thing and do what we need to with this, we first have to go ahead and draw the original point. So 0, 4 is the original f of x, the first value, and then 1, 1, and then, let's see, that's 1, 2, 3, 4, 4, 3. And so there's the original graph. Looks something like that. And again, I have no idea what this function is. All right, I have no idea what that function is, but that's my original function, f of x. From there, then, I want to take that function, and we're doing nothing vertically or horizontally to this graph. All right, so we're not going to shift the points at all. We're simply going to stretch it by a factor of negative a quarter. All right, well, the negative is going to take each of those points and reverse them. So we're going to flip this point down to here. We're going to flip this point down to here, and we're going to flip this point down to here. And so now, right here, is the first transformation where we do negative f of x. And now let's deal with the quarter. The quarter says take all of those points and multiply them by a quarter. All right, so 1/4 of 4 becomes 1. 1/4 of negative 4 becomes negative 1. 1/4 of 1 becomes negative 1/4, which is right in there somewhere. And 1/4 of 3, well, 1/4 times 3 becomes 3/4. So somewhere around 3/4, which will be roughly, whoops, not there, there. And so now when we draw our graph, I know you should probably be using a line tool there, but you can basically see that we've shrunk this thing. We've made it much wider because our coefficient was 1/4, which is a number less than 1.